So, greetings again. Let's continue our videos. We have given a couple of examples on free and dynamic response for different inputs, like step input or impulse input or different initial conditions. And in all of our situations, when we, ended up with some transfer function, the denominator was a polynomial, but always had, real roots of single multiplicity. So the question here is, what happens when we have zeros that have a higher multiplicity, right? For example, let's say we have 1 over s times s plus 2 squared or something like that, right? And what happens in this situation? How are we going to break down this fraction? Now, the truth is you are going to break down this fraction, let me write it a bit lower, by breaking down all of the individual terms of lower order. Okay. So when I'm breaking down this fraction right here, okay, oops, I'm sorry. I don't only have to include this squared term, right? I also have to include terms of lower order, right? So here in this general situation where some denominator appears, doesn't matter. Okay, now come on. And let's say we have some other terms right here. Okay, when I have a factor that is of the order r, what happens is that I break it down into all of the lower terms that appear. Okay, and the thing is now that it is a bit more tedious or difficult to compute each of these individual terms, like k1, oops, I'm sorry, k1, k2, up to kr. Okay, and I'm going to give you some examples. You will find also this formula right here in most of the books on automatic control systems. The idea is this: you always start by computing the higher order fraction. So actually here I'm going to start by computing kr, and then I'm going to go back until I reach k1. But this is a bit difficult to understand just by looking at this formula. So I'm going to explain this through examples. All right. So let's go into our canvas and let's start by solving the differential equation. Okay, so let's say I'm having this system right here. CFS, I'm describing it through a transfer function, and the system is s plus 1 of s squared plus 4s plus 4. And I'm trying to find the step response. Right, which means that I have a step input. Now let's start solving this system to see what happens. So the Laplace of the output is the transfer function multiplied by the Laplace of the input, which will give me s plus 1 over s multiplied by s squared plus 4s, oops, plus 4, right? So I need to find the roots of this polynomial. Oh, so let's see, d is equal 16 minus 16, this equals 0. So then the root is minus 4 plus minus 0 over 2, which gives us minus 2. So here I have a multiplicity, right, which means that the factorization is like that, s multiplied by s plus 2 squared. Okay, great. So now, when breaking down the partial fraction expansion, I'm sorry, we're going to break this down into all of the individual terms of lower order. So I have a and b and c, which is s plus 2 squared, right? Nice. So now I need to compute these three terms. And well, for a, things are very easy because we have already done that. So it's the limit as s goes to 0 of s multiplied by, I'm taking this whole rational function here. Right? So having 1 over 2. Nice. And then B and C are a bit more difficult to compute. So actually, C is not at all difficult. So I'm going to start from the end by computing C, the highest order term. So it's the limit as s goes to -2, and the idea is exactly the same. I include this higher order term. So this gets removed, and then I simply replace s -2 plus 1 over -2, which gives me minus minus 2 plus 1, it's -1 over -2, it's plus 1 over 2. Okay, so all is good. I'm sorry for this. Let me write it more clearly. That's better. Okay, so 1 over 2. And then we need to compute beta. Now, beta has a much different formula. It is actually the limit, again, as s goes over to -2 of what thing? Now, we are going to use the previous factor, C. And C, after looking at C, after we perform this cross out of the terms, I have this rational function remaining. Okay, and this is the rational function that interests me. So actually, the limit here is, let me move a bit lower. Okay, the limit here is s plus 1 over s, which are the factors that remained after this simplification, but I take once its derivative. Okay, so let's compute this limit. So s goes to -2. Let's do it step by step. So s plus 1, the derivative multiplied by s, minus s plus 1 multiplied by s derivative over s squared, which gives me the limit as s goes to -2. So we have s minus s minus 1 over s squared. So this gives me minus 1 over 4. Okay, so this is it. Okay, this is my solution. And does this look weird? It looks a bit weird, computing beta, but this is the process. Once you take a look into the formula that I showed you earlier, you will understand it much, much better. So even if we had higher order terms, we would continue the same way, but again, we would have to have a second order derivative, and also here we would have an additional term, an additional factorial. You will see it printed down in the formula. So let's see. Y over s is this. Okay, so y of s, I'm sorry, is this. We have 1 over 2 of 1 over s, okay, plus, minus 1 over 4 of 1 over s plus 2, right, plus 1 over 2 over 1 over s plus 2 squared, right? And now we need to take the inverse Laplace transform to obtain the solution. I'm sorry, the inverse Laplace transform gives me this. Okay, let's see. We have the solution being, we have, of course, 1 over 2 of the step input, right? And then, oh, by the way, I just noticed it's s plus 2 squared, right? So it's not 1 over 2. It's 1 over 4. Okay, cool. Cool. So it's 1 over 4 right here. Nice, and 1 over 4 right here. And then we have minus 1 over 4 of epsilon to minus 2 times t, multiplied by the step, plus 1 over 2, and then we have squared here, and this will give me t times epsilon to the minus 2t multiplied by the step in. Right. So this is our solution, and I can very easily plot it, pretty much using the same formulas as before. And this is time, of course. The system starts from 0. And here I have 3 terms. Okay, one of these terms is 1/4. All right, so the system will end up in a non-zero steady state. Okay, this term, of course, goes to 0 as time goes to infinity. And then a big question is what happens with this term right here. But if you remember from high school mathematics, this term also goes into 0 because this term basically is this fraction. So this goes to infinity as time goes to infinity, obviously, and this also goes to infinity. So we have a fraction where the denominator and denominator, both of them go to infinity. But since this is an exponential function, the denominator goes into infinity at a much higher speed. And this is why this fraction eventually goes to 0. Okay, so we have the addition of these three terms, and two of them disappear, and eventually the only term that remains is the step uh, term. Okay, so this system will not perform any oscillation. Of course, we don't have sinusoidal terms, but it will simply steadily over time go into the 0 position. Okay. No, the 0, I'm sorry, go to the 1/4 position. Okay, so this is it for our system. Okay. It's not extremely difficult to solve, but it gets more and more tedious if higher order terms are included. Actually, if you have 3 or 4 terms in the polynomial, let's say we had here like uh, s plus 2 to the third or to the fourth, it becomes really a pain in the neck to compute all of the uh, coefficients. Okay, so let's show you let's see another example. Going to use a different transfer function now. We have 2 over, I'm sorry, s plus 1, okay. And I'm looking for a step response again. So I'm going to perform the exact same thing in order to find the solution and multiply g of s by the input. So I'm going to end up with 2 over s times s plus 1 squared. And this will be broken down into 3 individual, what am I doing? Sorry. Big fractions. Then we have c over s plus 1 squared. Nice. Okay, so now we need to find all the 3 terms. So s goes to 0 for alpha. I'm going to use this exact fraction multiplied by s. This gets removed, and this becomes 2, right? Cool. So then we can have beta. No, since we have multiplicity, we are going to start from c. So c is the limit as s goes to minus 1 of s plus 1 squared or 2 of s plus squared. So this gets removed. So we have 2 over minus 1, so we have minus 2, right? And then b becomes the limit as s goes into minus 1. Let's move a little bit lower. Okay. Of what thing? Of this thing right here, of this term right here. So we have 2 over s derivative. So this is it. This is the limit as s goes to minus 1. What is this? S to the minus 1. So this is going to be 2 times minus s. No, let's think about it a bit clearer. This is 2 multiplied by s to the minus 1 squared. So this is minus 1 multiplied by s 1 over s squared, right? So this is equal to, let's move below. So this is equal to nice. Okay. So this is it. That's the whole idea. Okay. Minus 2. Sorry. I'm making a lot of mistakes today. I apologize. Okay. So this is minus 2. My apologies for making many mistakes. So now it is a bit late at night, so I'm getting a bit tired. So y over s, let's write everything down, is u 1 over s. Beta is minus 2 of 1 over s plus 1. And c is again minus 2 over 1 s plus 1 squared. Now, by taking the inverse Laplace transform, I can finally compute the solution. The solution is 2 times u of t minus 2 times epsilon minus t minus 2 times, and since we have squared here, I'm going to take t times epsilon minus t of u of t, right? So this is the solution. And again, I can plot it. This is very easy to plot because we have a fixed term, so I'm going to end up in this position. And then I have two additional terms, but both of these terms eventually go to zero. So they get completely removed from the response, right? So the system will start from zero, of course, and then it slowly but surely moves into the position of 2 and remains there. Okay. So this is the response of the system for this case. Okay, so as you can understand, this is very, very, very easy. But of course, it becomes exponentially more difficult, kind of saying, when we have more and more and more terms. So in the situation where you're going to end up having, let's say, this very, very complex differential equation, and you are going to take the step response, you are going to end up having far too many terms. So you're going to end up with something like this. This will give you a lot of terms. Okay, so you're going to go a over s plus b over s plus 2, c over s plus 2 squared, plus d over s plus 2 third, okay, plus e over s plus 1. Okay, and each of these individual terms, of course, will give you a different term, but this goes to epsilon minus 2 of u of t. All right, this goes to t times epsilon to the minus 2t ut, and this goes into t squared over 2 of epsilon to the minus 2t ut. So you see each time the polynomial coefficient goes from t squared, t third, and so on and so on. But of course, all of these terms are stable. They all go to zero since the exponential function has a negative factor. So any questions that you have, you can write them down below. You will find a lot of examples like that in the books, either in Dorf and Bishop or in the Norman Nice book. And any questions, okay, just write them down. But you need to start solving exercises yourself in order to become acquainted with the Laplace transform. Okay, that's for sure.